for the introduction. And of course, yes, questions are very welcome at every point. I will talk about braided fusion categories. My intention to make this like a mini course available to as many people as possible. So hopefully, those who did not see much of this before will learn something new, and hopefully people who did see things before will also get something useful. So the motivation for study such things is that many categories admit the operation of a direct sum and tensor product at the same time. And there are examples of such categories. For example, you can certainly do such things with representations, with complex representations of finite groups, semi-simple Hopf algebras, Lie algebras, semi-simple Lie algebras. And these things, they enjoy additional property called complete reducibility. So, in particular, if you tensor two objects, two such representations, let's say x and y, then the result can be, well, let's say irreducible. X, y are irreducible. Then the result is decomposed into direct sum of irreducible representations occurring with some multiplicities. That's a typical situation in all these settings for groups, semi-simple Hopf algebras, etc. Now, you can think about this as fusing together object x and y and obtaining a bunch of objects as a result of this operation. Okay, so this terminology was coined by physicists, and that stayed there. So we will call this fusion, and that explains the name of fusion category in the title. Now, it turns out that such structures occur in a wider context, even without underlying algebraic objects or vector spaces. Okay, and at least interesting things. So, this is the kind of the things I'm going to talk about. So before I proceed, we will need some conventions. I will use the language of categories and functors. So a category is a collection of objects, and functors are morphisms between them, satisfying usual associativity properties, existence of identities, etc. Now, the categories I will consider will be of rather special sort. So I will consider categories that are additive, that are direct sums. I would assume that they are abelian, so that one can talk about kernels and co-kernels of morphisms. Can talk about kernels, co-kernels. So in short, one is able to do sort of a linear algebra in this setting. Now, I will work over complex numbers, so my categories will be C-linear, meaning that every home space is a complex vector space. So each home xy is a complex vector space, and composition of morphisms is bilinear. Now, I will also, now a typical, one more thing, another property is that my categories will be finite. That's not, strictly speaking, absolutely necessary, but it will simplify things greatly. By finite, I will mean that there are only finitely many classes of simple objects, and all home spaces are finite dimensional. Now, to put these things in a proper perspective, you can always think about such categories in concrete algebraic terms. So a typical example of such a category that satisfies these conventions would be a category of representations of a finite dimensional algebra. So finite dimensional representations of finite dimensional algebra. I will not use this identification in my talk, but that's something to keep in mind. So this is the sort of categories we are going to consider. I will also assume, at least at most of the time, that categories are semi-simple. So, meaning that whenever you have a subobject of an object, then there is a direct complement. So this is an analog of this complete reducibility that I mentioned earlier. Again, most of the things can be done without some simplicity or finiteness assumptions. Certainly, I won't need them today, but I would stick to them eventually. And the reason for this is that I'd like to avoid technical difficulties, okay? So this theory is still in its infancy, and we are in the position that, you know, you would not advance to study Banach spaces until you understand finite dimensional complex spaces, right? So that's where we are at. Okay, any questions so far? There are all these nice microphones around, so if you feel like asking a question, grab a microphone and ask. Okay, so yeah, please. Let's just pass that.
This probably has no precise answer, but what do you think is the more difficult obstacle to come over, finiteness or semi-simplicity?
Well, I think finiteness is more essential.
More essential.
For what I'm going to do. Yeah, I'll give some examples that illustrate that. Yeah. All right. So now, let's get to the main definition. So I'll talk about well, tensor categories first. So by definition, a tensor category is a category with a bifunctor called tensor product, in addition to a direct sum that already exists like this. So category with such a functor, and the unit object, we will call this the unit object 1, along with the following data. Namely, I would like to require this tensor product to be associative. Now, in what sense? Well, so associativity would mean that I can form, well, no matter what, I can always form two products when I have three objects. I can multiply them in two different ways, right? So first x and y, and then z, or first y and z, and then x. So these are tensor products, not sums. Okay. Now, it's not natural from the categorical point of view to require them to be equal. Rather, we would require them to be isomorphic. But we would like to be able to control the way they are isomorphic. Okay? So we introduce a collection of natural isomorphisms called, denoted AXYZ, called associativity constraints. And similarly, the unit object plays the role of unit. So we will have isomorphisms between one tensor x and x. So we'll call this, and this is right. Again, same strategy. We do not want them to be equal. You will see that this is a too restrictive thing to ask. It's much natural to ask for the isomorphism. Now, this associativity, and these are called unit constraints. Now, these constraints are to satisfy certain conditions on their own. So, namely, you see, like, there are two ways to parenthesize the product of three objects, right? Now, if you come to four objects, then it's a basic counting problem to see that there are 5 ways to do this, right? So let me write them down. So there are 5 ways to have a product of 4 objects taken. So let me write them down. So this would be this. Another one, then I can also do, and what else? And this. Now, in general, if you have n objects, then the number of such parenthesizings is a Catalan number, right? That's something we teach students in the combinatorics class. So there are 5 ways to do this. Again, we want them to be compatible with each other, okay? But now we can travel between these different products using the associativity constraints, right? So for instance, here we use a XYZ tensor identity. Here we can use what? AX tensor Y tensor Z tensor W, right? Just moving the parentheses around using this constraint. So here, what do we use? It's x, y tensor z, w. Here it will be x, y, z tensor w, and here it will be identity tensor a, x, y, zw. Okay. Again, we don't invent anything. We just recorded the ways we can travel between these products. So, well, now you see that there are two ways to travel from this product to this product using associativity constraints. So you'd like these two ways to agree. Okay. So we require this diagram to be commutative. So this diagram commutes. And appropriately, this diagram is called the pentagon diagram. Okay, so that's how we define the tensor product. We introduce associativity constraint and impose condition on this constraint. Well, similarly with the unit object, it's now going to be simpler. For instance, you can form, let's say, this product, one product with x and y. Again, these three things have to be isomorphic, but they can be, isomorphic in two different ways. We require that these two different ways actually coincide. So here we use associativity, a1 xy. Here we use what? Left constraint of x. Here we use left constraint for x tensor y. There is a similar diagram for the right constraint. A triangle for the right constraint. All right. So now, well, then we can ask, of course, what happens if you have more than four tensor factors? Well, there is a theorem due to Maclane's coherence says that any diagram consisting of these constraints, associativity and two unit constraints, automatically commutes. The algebraic counterpart of this is that you only care about associativity of three factors, right? If you have more than three, then it doesn't matter how you place parentheses. So this is the categorical version of that. Now, categories are meant to be studied not in isolation, but together. So we should talk about tensor functors. So a tensor functor between a pair of tensor categories, C and D, will be what? Well, it should be a functor that preserves the given structure, please.
Should it be a unit x equals 1 in the middle as well, or does it follow?
Yeah, it follows. So there is one that I omitted, with the right, and the one in the middle is the consequence of the other two. Yeah. Okay. So yes, a tensor functor should be a functor that's compatible with tensor product. So we should be able to compare this and this, where x, where here is a product in C and here is a product in D, right? Again, using the same idea as before, we do not ask for them to be equal. We ask for them to be isomorphic. So we have a collection of natural isomorphisms, and these natural isomorphisms are to satisfy their own coherence, which would be a good exercise to produce. Again, you would have to deal with three factors, right? And there is only one sensible diagram that you can draw. Okay, so satisfying certain commutative diagram. I will draw more commutative diagrams today, but some of them I'll have to speak. Otherwise, you would not see anything else. All right. Now, so this is the notion of a tensor category. Now, we will need something else. So we will need, in these examples that I gave, representations of groups, Hopf algebras, there is always a way to produce the dual representation, right? The dual vector space. Please.
Information imply f of the unit and the unit would be isomorphic, or do we need that additionally?
Yeah, there are different versions. Yeah, thank you for asking this. Yeah, so one would, yeah, I was told that this thing kind of slides down. So yeah, one would like to impose, in addition, an isomorphism between the so there are different versions, regarding this. If it's not an isomorphism, it's called a Lutz functor, etc. Yes. So this is a necessary requirement. So what I will think is that one has the notion of a dual, which is in this kind of linear algebra examples is always the dual vector space. Here comes the first difficulty. The way we defined a tensor category doesn't presume existence of any underlying vector spaces. So you cannot simply write things like this, okay? What you do instead, you introduce duals axiomatically. So introduce dual objects axiomatically as follows. So given X and C, an object in C, its left dual is an object called it X star, along with two maps called evaluation and co-evaluation. So evaluation of X is from X star tensor X to 1, keep it like this, and co-evaluation is from 1 to X tensor X star. Now it's a bit confusing, but also I think one can remember that for the left dual, the star is on the right. That's, well, you can say that X is on the left. Anyways, so this is called evaluation, and this is called co-evaluation. That are to satisfy a compatibility condition. So namely, what you can do, we can have this composition. So for X, we can go to X tensor 1 tensor X using the left constraint. Then you can go from this, let's say other way around. So X tensor 1 right constraint. Then from here,
so it was okay.
it was okay.
At the beginning,
Yeah. Okay. I was too busy holding the board. So yes. So how was it? So left was in the beginning. So it's 1x. Then we can apply co-evaluation, and it would go from here to here, and then we can use associativity, and then we can apply evaluation to get X tensor 1, and then the right constraint will give you back to X. Okay, so now this is required to be identity. So again, so the idea is this: we introduce this as axiomatically. We define an object such that certain structures on it exist. Okay. Say again? That's right. Yes. So it is unique up to an isomorphism. All right. So because you see, like there is certain freedom in choosing this morphism. So you can multiply this by a scalar and multiply this by the reciprocal of a scalar. They will cancel each other. So these maps themselves are not so important. It's important that they, that the choice of such things exists. So yeah. So if the left dual exists, it is unique up to an isomorphism.
There are other diagram with the dual.
Say again?
Another diagram with the dual, because you have this for X, but you have other with X dual.
That's right. So I mean, I said here a left dual. There is also a notion of the right dual.
No, but for each one there are two diagrams that are identical.
Yeah, that's right. Yes.
Yeah. So
Yeah.
it's only one.
That's right. Yes. So I'm sorry. Yes. So there is another one that starts with X star, and then it would go like this. So it would be X star tensor 1, and then it will be X star tensor X tensor X star. Again, let me skip associativity to keep it reasonable. And so then, so this will be what? This will be co-evaluation. Then you have evaluation, and you have 1 tensor X star, and this is X star. Yes, very good. So there are two diagrams, and this is required to be identity of X star. Now, well, in addition to this, there is a notion of the right dual. There is a similar, you see, like this, notions are not symmetric. Here duals come on the left, here it comes on the right. Yes. So you can flip that, yeah, and get the notion of the right dual. Yeah. Okay. So there is a rather unfortunate name for such categories. A category that has left and right duals is called a rigid category. A tensor category with left and right duals is called a rigid category. Again, unfortunate name because it doesn't explain anything. There is no like way to interpret this as a sum of rigidity, but this name was given. We have to live with this. So now, so what would be an example and why these maps are called evaluation and co-evaluation? Let's take the simplest possible category, the category of finite dimensional complex vector space. Well, here, of course, as we know very well, the dual of an object V of a vector space V does exist. And our evaluation map is what one would expect. So you take what? You take a functional and a vector and evaluate one on the other, right? You get a scalar that is an element of C. Co-evaluation. Now, co-evaluations should take as an argument a scalar and return an element of V tensor V star. Well, when we apply it to one, we set it to be like this. So Vi tensor Vi star, where Vi and Vi star are dual bases. A dual basis of IV and the star respectively, so that when you evaluate, one vector of one basis on another, right, you get one only if indices coincide and zero otherwise. Yeah. So now this illustrates like the importance of finiteness, the question that was asked to me before. Look, we would not be able to do this if V was infinite, right? So the finiteness is therefore important for the rigidity, and that's a strong property. Of course, the same works, for more general categories, such that representations of a group or a Hopf algebra. Now, it also should be noted that that existence of duals is not guaranteed. Okay. However, when they exist, it's a property rather than additional structure. Right? Category, it's either if it's rigid, then it's rigid in one way, right? So now I can give the definition. So a fusion category is a semi-simple tensor category with all these properties that I mentioned, such that which is rigid and such that the unit object is simple. So if this condition is dropped, then the category is called a multi-fusion category, which can also be studied equally well. Now, I already mentioned some examples, and there will be many more, but for today I will be content with elementary examples, so more examples. Let's see what I mentioned. I mentioned representations of groups, etc. You can take the category VG of G-graded vector spaces, where G is a finite group. So this is just these are vector spaces with decomposition labeled by elements of G. And the tensor product respects, this grading, because we usually tensor graded vector spaces. Okay, now let me deform this example a little bit to show that the associativity constraint can be non-trivial. So here, when I talk about G-graded vector spaces, of course, I assume like the usual associativity constraint, right? So something like this, X tensor Y tensor Z being X tensor Y tensor Z, like this. But it doesn't have to be this way. So namely, let's say alpha be a function on the cube of G, which is a tricocycle. By definition, it's a function of sorry, not C3, C-multiplicative. Be a tricocycle. So that's a function that satisfies the following conditions. So W, X, Y, Z wx, sorry, I call it alpha, alpha x, y, z, w, alpha y, z, w equals alpha x, y, z, w times alpha x, y, z, w. Note that this equation was already written on the board here, right? That's how you would read this condition, right? You have the same very situation, right? Triple product on one side, double product on the other side, and the values of argument are the same, right? So we can use this to define a new associativity on Vec G. So namely, what I'm going to do, I'm going to take this map, and now on homogeneous spaces, let's say Vx, Vy, Vz, this will be omega, let me put here a tilde, omega x, y, z times this usual associativity, right? So in other words, I'm introducing here a scalar. Huh?
You put W, it's alpha.
Oh, it's alpha, yes, thank you. Alpha, yes, alpha like this, right? So this is the usual associativity. Okay, again, immediately it follows that this tricycle equation translates into the pentagon diagram, right? So that's a good way to think about what's going on. That's what we are generalizing here, right? So it's kind of, can think of this as non-commutative cohomology. All right. Yeah. So these are like the components, right? So every space, is a sum of homogeneous components, right? So I'm going to define this in the situation when I have homogeneous components and then extended by linearity, right? Yeah. Okay. So next I will talk about dimension theory. There are various notions of dimensions, and the one I will introduce is called the Frobenius dimension. So I might need other dimensions later on, and I'll introduce them as needed. So let's see. So let xi, say I from 1 to n, be a simple objects of C. Well, when I say that, I mean that I choose one representative of each isomorphism class of simple objects. Then if I pick an arbitrary object x and tensor this with xi, then the result for sure will be a linear combination, well, will be a direct sum of some objects xj, well, possibly with some multiplicity. So I introduce this multiplicities like this, nx, ij. So where n, x, ij are non-negative integers, right? So each object can come with certain multiplicity. Now, so what we do in the process, then to an object x, we assign a matrix, right? I denote it like this, nx. So this is the n by n matrix with non-negative integer entries. So there is a classical result, a theorem of Frobenius and Perron, that tells you that such a matrix has a non-negative eigenvalue that dominates other eigenvalues in absolute value. So there is a Frobenius-Perron theorem tells you that allows you to take the largest non-negative real eigenvalue. In fact, it's strictly positive. And the reason for this is that such a matrix cannot be nilpotent because of the rigidity. Otherwise, the rigidity would fail. So, and let's call it Frobenius-Perron dimensional facts. This dimension behaves well with respect to tensor products and direct sums. So Frobenius-Perron dimension of a direct sum is, of course, the Frobenius-Perron dimension, the sum of Frobenius-Perron dimensions. And similarly, Frobenius-Perron dimension of the product is the product of Frobenius-Perron dimensions. This is not entirely obvious. It would require application of this theorem that I mentioned, but that also characterizes this dimension. There is a unique homomorphism, that takes that sends each object to a positive algebraic integer. Okay, so now again, so this dimension takes values where? Well, it takes values in real. And the good news is that in familiar examples, this dimension Frobenius-Perron dimension coincides with the usual dimension. So, for example, if V is a representation of a group G, then Frobenius-Perron dimension of V is the same as the vector space dimension of V. One can also use this dimension to introduce the dimension of the whole category. So we set the Frobenius-Perron dimension of a fusion category to be a summation over simple objects of the squared Frobenius-Perron dimensions. Again, as one would expect, for instance, for Frobenius-Perron dimension of representations of G or G-graded vector spaces, one gets what is expected, an integer equal to the order of the group. But the important new feature is that in general, such dimension doesn't have to be an integer, which means that there exist categories that are truly different, from the classical categories. Okay, so the smallest such an example, and we'll see more of them later on, is so-called Ising category, and it has three simple objects, one, A, and X, and the following product rules. So here are A tensor A is identity, X tensor A tensor X is X, and X tensor X is 1 plus A. Now, using this definition of Frobenius-Perron, it's very easy to see that there is only one homomorphism, and the Frobenius-Perron dimension of X is the square root of 2. Because invertible objects, of course, have dimension 1, so this tells us that the square of dimension is 2. Now, incidentally, these rules that govern the multiplication of simple objects are called fusion. Here, of course, it's enough to know it for X simple, right? So there is a bunch of, in other words, there is an underlying ring, that governs the multiplication of simple objects in the category. It is important to stress that these fusion rules themselves do not determine a fusion category. So if you can produce, formulas like this, this doesn't guarantee that associativity constraints do exist. And it's hard and, sometimes actually solvable problem to determine which fusion rules actually are realizable by fusion categories. But one thing that I can mention is that there is the finiteness result. So given a set of fusion rules, let me duplicate this formula, something like xi tensor xj xk. There are at most finitely many, and possibly zero, fusion categories with these fusion rules. So this statement is known as the Opniano rigidity. So what it means is that there are no deformations of fusion categories. There are no continuous families. They're all discrete. And this is a good news, of course, because it makes their classification possible. All right. I also want to mention another example of a non-integral category. So in this case, the Frobenius-Perron dimension of the category would be what? 1 plus 1 plus 2 is 4. Now, even there doesn't have to be an integer. So another example would be so-called Fibonacci category that has two simple objects, 1 and X. with the fusion rules that x tensor x is 1 plus x. In which case, the Frobenius-Perron dimension of x, by solving the quadratic equation, it has to be positive, remember. So it is a golden ratio, the golden ratio. And the Frobenius-Perron dimension of the category in this case is the sum of squares, which is what, 5 plus square root of 5 over 2. Now, these categories are not mysterious at all. They come from, representations of a quantum SL2 respectively at the 4th and 5th roots of unity. So the square root of 5, this represents the appearance of the 5th root of unity. We'll talk more about this. Okay. So next, and that's really already close to the subject of my lectures, I'll talk about braided categories.
A question for each. So you mentioned finiteness. In this case, only 2 up to tensor equivalence.
Okay, so the number of simple objects is always finite, right? So here, like for instance,
No, I mean,
Yeah.
Fibonacci category case. These 2 exhaust all possibilities.
all simple objects.
No.
That-
Fibonacci category, you have a finitely many fusion categories, right?
That's right. Yeah. Well, I did not. Well, I was asking whether these are all the categories of this type or what.
Hmm?
Is this your question? Are you asking if this is the only category? This is simple.
Example, you have 2 examples, right? Here,
That's right.
4th and 5th root of unities. Up to equivalence, they are all.
Well, no, I mean, like if you pick like different root of unity, you'll get different category with different number of simple objects.
He asked if there are other.
Okay. Well, yes. So, like one thing you can do, you can take the Galois conjugate of all the morphisms. Okay. So there is kind of operation of a Galois conjugation.
There is no lie.
Galois conjugate is negative, I think.
Okay, so like, once you write down like all morphisms, in a certain basis, they would depend on the square root of 5. Square root of 5 will show up. Now, if you apply the Galois conjugation, the square root of 5 will become negative square root of 5. You'll get a different category with the same fusion rules. Even without this, for the Ising category, this is not the only one. There are, if I remember correctly, I think there are 4 categories with this fusion rule.
So there exists other.
There exists other, but finite remain.
Okay.
And typically, it's not an obvious question. There can be 0, there can be 1, but finite remain in any case. So, braided categories. Well, let me first say that in general, tensor product of 2 objects certainly depends on the order. So x tensor y is not isomorphic to y tensor x, for example, in the category of G-graded spaces when G is not abelian. In this case, tensor product is just the multiplication in G. Now, we would be interested in categories when x tensor y is isomorphic to y tensor x. So we define a braiding on a fusion category C is a natural isomorphism xy from x tensor y to y tensor x for any pair of objects. And again, we do not stop here. We do not just require them to be abstractly isomorphic. We would like to be able to control how they are isomorphic. So this isomorphism is called the commutativity constraint. And as the name suggests, it's a close relative of this associativity constraint. Now, what do we want from it? Well, let me explain this informally. So, look, when we permute x with a product of 2 objects, we can do this in 2 ways, right? We can permute it with a product at once, or we can permute it with each vector individually, right? The result should be the same. Now, one can draw a diagram like this. So, let's say we permute x tensor y with z. So, what we can do? We can permute, make sure I draw the right diagram. So, we can apply associativity ax y z. So, it will be x tensor y tensor z. Then we can permute x with y tensor z. So, it will be y tensor z tensor x. And then we can apply associativity again to get y tensor z tensor x, y z x. So this is the situation when we permute X with two objects at once, with the product at once. We can do this step by step. Permute X and Y, no. Permute X and Y, so it will be Y tensor X tensor Z. Then we want to permute X and Z, where we have to shift the parentheses, apply associativity first, A, Y, X, Z, it will be Y tensor X tensor Z, and then we can permute X and Z like this, right? So pay attention, you might as well disregard associativities for time being and pay attention to this, right? So it kind of behaves like a linear form would behave, right? So there should be, of course, a kind of symmetric diagram, which I will omit, plus a similar diagram when we permute, like object with the product on the right? Or like C, Y tensor X, Z. Again, it should be clear what I mean by that, right? Okay, so now, examples of such things. Well, first of all, familiar category, G, has a usual symmetric braiding, namely when we take a pair of objects, V and W, and vectors, pair of representations V and W, and vectors, and then we permute, then we have this. Now, not every braiding is as simple as that. There are other non-trivial things, non-trivial braidings, and they are more interesting. So here is more interesting example. Let's consider the category of A-graded vector spaces, where A is an abelian group. It has to be abelian, otherwise, of course, there is no possible braiding. Now, in this case, you just look at these axioms, and you realize that a braiding on this category is given by a bilinear form, multiplicative bilinear form on A, where I can describe braiding by as what? So look, it will be convenient if I identify simple objects with elements of A here, right? So then the braiding of C X and Y will be B X Y identity X tensor Y, or X plus Y, like this. Okay. Again, this axiom kind of manifestly tells you that you need linearity in both arguments, right? Now note, so first of all, there are many bilinear forms in a given abelian group, and this bilinear form differ from each other. Some degenerate, some are not, right? So we will have this property later on. Now, there is a more general statement, namely, if we say that a fusion category is pointed, if all its simple objects. A typical example of such category is this category I constructed earlier, where G alpha. The category of G-graded vector spaces with twisted associativity constraint. Now, classifying all such categories amounts to computing, the Total homology of all finite groups, which is a hard problem in itself. Now, for braided categories, it's easier. So if C is braided pointed, then there is a thing we can do. Look, then for each, first of all, invertible objects of C form an abelian group. Invertibles of C is an abelian group. Furthermore, if you have an invertible object, then what we can do, we can assign to this object its self-braiding. So we can permute this object with itself, right? This would be what? So braiding is from X tensor Y to Y tensor X. This would be from X tensor X to itself. So this would be an automorphism of X tensor X, which is again a simple object. So this is an element of the multiplicative group of complex numbers. So this assignments, this defines a quadratic form. I'll give it a name called like Q. Quadratic form on Q with values in the multiplicative group of the field. Conversely, so given such a quadratic form, one produces a pointed braided category. So there are two statements here. One, that the resulting thing is a quadratic form is an easy statement. It could be directly checked from the definition of braiding. This is something well known. This is a theorem of Ellenberg and McLean, and it's less obvious and requires some work. But the bottom line is that pointed braided fusion categories correspond to quadratic forms on abelian groups. Now, these things are easy to describe. Also, this fact brings an important geometric insight into the theory. So quadratic forms are geometric things, right? You can study things like orthogonality, isotropic spaces, etc. All these have counterparts in the world of categories. And that's what I plan to talk about tomorrow morning. Right?
Okay, bang on counting.
I have only 1 hour lecture, right?
Yes, you can take a bit longer if you like, but
That's fine.
an hour is
I
good.
like to,
We don't actually have afternoon tea for another half an hour, so
that's
you can take as much time as you want to ask some questions.
What does it? It was quick at the end. What does it mean to be invertible for an object?
So invertible, yes, a good question. So invertible with respect to TensorFlow. So you X is invertible if this thing is actually isomorphic to 1. So in which case evaluation and correlation maps are isomorphisms.
Okay.
You see, if inverse exists, it must be like this because of the evaluation.
And second question: why are the automorphisms of X tensor X equal to C star?
Because if X is simple,
It's Schur-Lemma.
Schoen's lemma, of course,
Okay.
yes. So we work over C, which is algebraic closed field, yes. So
Okay,
X,
thank
Y
you.
are simple, then of course X tensor Y is simple, right? Otherwise, if this can be decomposed, then we can decompose. Sure. Sorry, I'm not simple, invert. X tensor Y invert.
More questions? Simon, grab the microphone.
So you had the associativity morphisms basically be 3 cocycles in the graded vector
Right.
space example. How general is this? Is this like really specific to graded vector spaces, or can you always get your associators as like some solution to some cohomology?
Yeah, it is like, okay, so this is what I was saying. So if you unfold this axioms of a braided category the way we unfolded it right here, right? So then you get like 2 conditions. So you get like omega, sorry, not omega, alpha, I called it, from a function of 3 arguments, and this C, a function of 2 arguments. They are related to each other. Now, this has to satisfy pentagon, and they together have to satisfy 2 hexagons. Now, this is not a new thing. So this is what is called an abelian 3 cocycle by Lindbergh and McLean. So it's related to this classifying space Ka2.
Yes, but this sort of used that in the example of graded vector spaces. I mean, you actually had this cocycle condition for groups. But if now you're near some different abstract category, then the set of simple objects is just a set, right? Doesn't necessarily have any
Yeah,
details.
I mean, of course, yes. So
But that still
yeah,
exists.
I mean, it's just like it's. I think it's just a useful analogy to think about what happens in the pointed case. In general, of course, it's very much far from this, right? So this maps are no longer scalars. They can be turned. Well, one can turn this into like linear algebra, but at a cost. Namely, one can form quite a like certain nonlinear equations that would express this. They go under the name of 6J. Symbols. So these are certain matrix equations that involve lots and lots of data. This is how one would put a fusion category into a computer and then try to solve these pentagon equations in this way. It's a hard problem, sometimes possible, and if you do like some smart things, then you can actually solve it sometimes. I don't know, maybe Emily will talk about something similar, related to diagrams in tensor categories. Yeah, but it's hard. It's goes well beyond the cohomology.
I have another question.
Microphone.
At some point when you define the Frobenius Perron dimension, you say it was unique up to some constraint, maybe.
No. Okay, so it is unique in the form. So there is a theorem of Frobenius and Perron that tells you that if you have a matrix with integer non-negative entries, okay?
No, I know
Yeah, yeah.
why they exist, but you say at some point where it has this property with direct sums and
Yes.
tensor
so-
product, then there is the unique function that blah blah
Yeah.
or something. I don't know.
I didn't say blah blah.
No,
Okay, no, I mean, okay, so what you have, I didn't, it's okay, so, well, we should give this a name, so, like, what I have, so, you know, this fusion rules are, like, put together, form a ring called the Grothendieck ring, ring of C, you know, well, it has a basis consisting of simple objects and, you know, the tensor product and direct sum this like this. So what I was saying is that Frobenius-Perron dimension is a homomorphism, is a ring homomorphism from the Grothendieck ring to the field of real numbers, and it has the following characterization. It is a unique ring homomorphism such that that takes every object to a non-negative to a positive real number.
it's a unique.
It is unique with this property, right? It's also a consequence of the Frobenius-Perron theorem.
Okay.
And Frobenius-Perron theorem tells you that it actually exists.
No, because Frobenius-Perron, I think it has some uniqueness when you actually ask to be positive, not negative. The matrix here can have zeros.
But that's exactly what's happening. So we are choosing Frobenius-Perron dimension of X to be the largest positive real eigenvalue, and
Yeah.
such things do exist.
Yeah, but it might not be unique if you admit zeros in the matrix.
Well, what do you mean? Among like finitely many positive integers, there is the largest one, right? So it is unique.
Yeah. I don't remember.
Yeah,
but there
it
was
cannot be
some-
zero, okay?
Yeah.
So the trivial part, it's not zero because you cannot have like this, you know, this cannot, it's not going to be zero as
Yeah.
long as X is not zero. And the reason for this is the existence of evaluation and co-evaluation maps.
Okay. In particular, if you have a subfunction category, the Frobenius-Perron dimension behaves well.
Yeah.
For example, if you compute it in the big category or the small category, it should be the same number.
What do you mean big and small categories?
Because suppose you have a function category, right? You have a subfunction category, so you choose some simple
Yes,
objects,
yes.
yeah, and they behave well, right?
Well, there is something like Lagrange's theorem, dimension of subcategory divides the dimension of the category.
I mean, behavior well in the sense that you take tensor products of two simple objects in this subcollection, they are the sum of just this subcollection, right?
Yes. Yeah, there is no
Now-
subcategory. Yes.
Now, if you try to compute the Frobenius-Perron dimension of some object in this,
Okay, yeah, that's
It
the
can-
same, yeah.
it should be the same.
It's the same, and that's the reason for this, right? So that's the restriction of such a homomorphism, you know, is the unique.
Is also
Yeah.
homomorphic. So
That's
should
right.
be
Yeah,
unique.
so you know, the restriction of Frobenius-Perron dimension to a subcategory is the Frobenius-Perron dimension. to a
Okay,
subcategory.
okay,
All right?
thank you.
Can I ask something related, which is probably quite naive? So having a real eigenvalue, is that just guaranteed by Frobenius-Perron, or do we?
That's right. That's
Symmetry
guaranteed by
of matrices.
Frobenius-Perron. So as long as you have matrix with non-negative real,
So we don't need the matrix to be symmetric. We don't need a
No.
braiding.
we don't. Yeah,
Sure.
that's right.
Any more questions? Oh,
Yeah.
behind.
Yes, please.
Who's got the mic?
Is it possible to generalize this result, this remark with K A2, for example, you have
Yes.
copy type
There is, yeah. So
Pn or
yes. So
open some n.
that's right.
So
Yes.
how to
So
generalize
I mean, okay. So my talk will be limited to fusion one categories, but there are things like fusion two categories that kind of are gaining popularity. Okay. And so if you want to consider, you know, like point to two categories, then you have to raise like this thing by one. Okay, each time. Yes, so they have this interpretation.
But you still have abelian for
Yes, of course, yes.
And for non-abelian, it's
No, I mean, of course, you know, like this only makes sense.
higher.
K-A-N for n
Yeah.
bigger than one only makes sense for abelian A, yes. I mean, it's a paper of, you know, very useful paper, but also very hard to read by Ehrenberg and MacLean from 1940s, you know, where all these things are described.
There was another question behind you, if you could pass back.
Yeah, so yeah, this is kind of a question because people kind of forget all the unit stuff and never really talk about it. My question is like, when you twist vec G by this 3 cocycle, right? You get the pentagon, right? Because
That's
that's,
right, yes.
what the 3 cocycle does. But it messes up the unit axioms a little bit, right? So what's the best way to deal with that? Like, do you modify your
Yeah, I think what you do, you normalize. Yes, that's a good question. So what you do, you normalize the 3 cocycle by the condition that if one of the arguments is 1, then it's equal to 1. So like you want to have things like this. And this is always this can always be achieved because any 3 cocycle is cohomologous to such things. So I didn't mention it, but it's certainly, like it's not just 3 cocycle, it's a cohomology class. If you replace alpha by cohomologous thing, you get an equivalent category.
Right. So that's what you would do. You would just
you just normalize this, but every cocycle is cohomologous to normalized one.
Right.
Yeah.
Any other questions? Right, if not, let's thank Dmitri once
Thank you.
more.